Is my slide visible?
Yes, sir.
Okay. So last day what we discussed about fiber optic link, let us go through it. Fiber optic link, then uh, what do you mean by fiber optic link and what are the other issues? Then we discussed about light source, LED and laser. Then we discussed more on it. What are the different types of semiconductor light source? Then we discuss about fiber medium. There are three windows in which we can operate the optical fiber so that we can transmit the information, transmit the signal in particular wavelength range where we get less loss as well as less dispersion. So there are three windows, 800 nanometer windows, 1300 nanometer and 1550 nanometer windows. Then we discussed about how the charge carrier movement takes place in light emitting diodes or particularly light source, semiconductor based light source. Then photo detectors we discussed how the electron and hole pair contribute to flow of current. Then we discussed what are the types of photodetector, and we have seen that photodetector output is very low, weak signal. It is weak signal, so we need amplifier to amplify it. So then we discussed what do you mean by optical transmitter link. Then we discussed what are the different types of optical fiber. So there are different classifications based on material, based on mode, based on index profile, and then other types of optical fibers like photonic crystal fiber, dispersion compensating fiber. Then we discussed what do you mean by single mode and multi-mode, and light propagation, how it can be explained, like using rays and waves. Then we discussed about slightly on modes, like linearly polarized modes. All this thing we will study in the theory. Then we have seen what is V parameter, what is the equation of this, and we have seen how the single mode fiber is characterized, like if V number is kept, single mode fiber only LP01 mode propagates, and LP01 modes always propagates irrespective of the type of fiber. It will not propagate only if core diameter is 0. In cladding, it cannot propagate only if its core diameter is 0, then the light cannot propagate. Then what is the equation of numerical aperture? We have discussed. Then what are the different values of V number for which the LP modes propagates? This LP modes only propagates in optical fiber, and basically in optical fiber hybrid mode propagates EH or HE modes because it is cylindrical fiber. So in cylindrical waveguide, only all modes propagates, and exceptionally the hybrid modes, that is HE and EH, both electric and magnetic field, are present in the transverse direction of the light propagation. Then we discussed about SWAT step index and graded index fiber. Okay. So now we'll discuss about
Sir, excuse me.
yes.
Sir, could you please record the class, sir, so that we can see it afterwards for recollection, sir? Revision. Thank you, sir.
So almost all the basic topics or basics concept I have discussed in the previous class. So today I will explain briefly about the experiments. So first experiment is setting up fiber optic analog link and setting up of fiber optic digital link. So basically you see that fiber optic analog link, what happens? We transmit analog signals. Okay. So there is one transmitter. So here, like say, if you use transistor and here one LED source we use, then it is plus VCC say, and this is LED. So if this is your input signal, if you apply sine wave, okay, so the current will vary accordingly through the transistor and intensity of the light will change. Okay. So that optical fiber will be connected uh, in front of the light emitting diode. Okay. This is optical fiber in front of the light emitting diode. Okay. So here there is actually it is P versus I. Okay. The characteristics of current. Okay. This is current and this is light intensity. So it is linear. So according to the input signal, the intensity will change, intensity of light will change. So that intensity modulation, basically intensity modulation takes place in optical fiber, and here one photodetector will be used. Photodetector is reverse biased. Here one minus some voltage, say minus V is applied, and across some resistance or load circuit, output say it is resistance R. So this is the light will be then in place in front of the optical fiber, you just connect the photodetector, which is reverse biased. Then the current will flow across the load resistance. These are the simple basic circuits. Now in analog link, generally we transmit analog signals and certain simple LED, okay, we can apply if it is a multi-mode fiber. If it is a single mode fiber, we use laser diode. In place of single mode fiber, we use laser diode, and in case of multi-mode fiber, we use light emitting diode. And depending on the wavelength, and for particular this experiment, we have used 660 nanometer LED. That means it is a red light LED. Red light LED. So here the analog signal at the output of the optical fiber, this change in the intensity of the light will be detected by the photodetector. And across the load, we'll get the sinusoidal signal. These simple basic concepts, nothing difficult is there in analog link. Okay. So in case of analog link, we use signal to noise ratio, okay, SNR is the performance criteria. Signal to noise ratio. And another important thing is that what I was discussing is what thing you have to do. You have to uh, make one table. Okay, say input signal. Input signal. Say if you input signal, if you say 2 volt peak to peak, let us say, and vary frequency. Vary frequency. So you make one table like normally people do. Okay, that is frequency versus gain or output voltage. V out by V in. So here make one another column. Let us say frequency versus output voltage. Then you take different frequencies starting from say 10 hertz to 100 kilohertz, 500 kilohertz, 1 megahertz, okay, 2 megahertz, like that. So it is a long range, quite long range of frequency, and you calculate different output voltage, okay, at the receiver end. Okay. So you calculate the gain. So what we will get, you have to plot this in a semi-log graph paper. You have to plot this in a semi-log graph paper, okay, and you will get this kind of response. Okay. So now say this is 0 dB. Actually, it will not be 0 dB, lesser than that. Now there are 2 points, and this is frequency. So it is a frequency response graph. So what we will do, we plot frequency versus gain. frequency versus gain, and there are 2 points you have to calculate. One is 3 dB frequency, is minus 3 dB, and another frequency you have to calculate 6 dB, minus 6 dB. Okay, so these two frequency you have to calculate. Let us say this is F1 and this is F2, these two frequencies. From the you may get points arbitrarily, but they have all some pattern of this low pass kind. You have to draw this way. Those points may not lie on the axis on one straight line, but they have some pattern that you have to follow and draw it. So generally this way any frequency response graph is drawn. Okay, so there are two frequencies that tells about bandwidth. So this is the 3 dB frequency that tells the electrical bandwidth. That is electrical bandwidth. And this F2 is the 6 dB frequency, and this is called optical bandwidth. So why this is electrical bandwidth? Electrical bandwidth means electrical power gets halved. That is electrical bandwidth. Why it is coming red? Okay, let me make it black, or slightly I increase the size of the slide. Okay, so this is electrical bandwidth. Electrical power gets halved. That means electrical bandwidth. Generally, this is the definition of any bandwidth. And optical bandwidth means optical power gets halved at that frequency. So this is so because what we do, this gain is what? This gain is what? V0 by V in. Okay, that means ratio of voltage. Okay, so if V0 by V in is, that is 10 log or 20 log, 20 log of this. So that means it is electrical power. Okay, P electrical actually varies as voltage square. Okay, so 20 log of V1 by V in actually 10 log of V output square by V in square. So that means it is at this point, at this frequency where the electrical power gets halved, that corresponds to electrical bandwidth. So voltage square, ratio of output voltage square by input voltage square. Now if you consider optical power, generally optical power varies as directly voltage, not voltage square. Okay, so when this ratio 20 log of P 20 log of P optical output and P optical, which is not electrical output, is optical output and optical input. That time it is half. So this corresponds to 6 dB. Okay. And this corresponds to 3 dB. Clear?
Yes, sir.
Okay. So now these things you have to calculate for this experiment: electrical bandwidth and optical bandwidth. Now the second part of the experiment is, you can see that it is a fiber optic digital link. Fiber optic digital link. So in this case, digital link will send only transmit digital signal, and maybe there is change in the transmitter and receiver circuit. Okay, you know that in case of digital signal transmission, okay, you have to decide the threshold, little change. Okay, so in transmitter receiver circuit, little change. So you have to take the decision. Generally, the detected output, if you send that input signal digital, now detected output is digital. Okay, detected output is analog, like this kind of signal. You are applying inputs square wave. Okay, but while after at photodetector output, and this is the input to uh, transmitter. Okay, and this is through optical fiber it is propagating. Okay, this output at the fiber end. Okay, this is generally electrical analog. Okay, fiber end or receiver or photodetector. Output at the fiber end or photodetector is generally analog. So you have to decide that which logic level it is. Okay. So it should be passed through some decision circuit. Okay. Decision circuit, so that this should be converted to square wave. So this level decide some threshold level. Okay. Threshold level is generally taken at the middle. So it is a V threshold level. So if the signal becomes more than the threshold level, that time it will predict as logic 1. If it is lesser than that, it will assume as logic 0. So there is some difference in the receiver circuits in case of digital link, and transmitter circuit more or less same, but it may depend, it may change, because in case of analog, the transistor biasing is required. You know that biasing circuit is required so that the operating point should be kept at the middle. Okay. And transistor current flow should be in only the active region, not in the cutoff or saturation region. No. So to ensure that, you have to use some biasing circuit in the case of analog signal transmission. And digital signal, no biasing is needed. Simple transistor you can use, okay, in case of digital link in the transmitter. But in case of analog circuit, you may need biasing circuit for transistor. For digital link, it is not required. So only on-off kind of switching is required, okay, for transistor. But at the receiver, this extra additional thing, that is decision circuit, is required. And apart from this, lot many issues are there. Now, the main drawback in transmission of digital signal in optical fiber is that uh, uh, pulse broadening. Pulse broadening in case of digital signal transmission. In case of digital signal transmission. Okay. So this is main drawback in optical fiber. Whole optical fiber communication, pulse broadening is the main drawback, and this is actually due to fact that dispersion. Okay, dispersion. Dispersion, you know that if many wavelengths travels in a medium, or many carrier frequencies travel in a medium, then they reach at the receiver at different times. So if they carry one optical pulse, one input pulse, let us say, that input pulse will reach at different times through different carrier, through different wavelength at the fiber end. So in time domain, what will happen? Actual signal, what will be detected, that is superposition of all these signals. So generally, the faster signal, faster wavelength reach fast, slower wavelength reach slow, okay, last. Slower wavelength, slowest wavelength reach last, faster wavelength, fastest wavelength reach fast. So if those wavelengths, and in between many wavelengths are there, and if those wavelengths reach at the fiber end, then they create pulse broadening. What is pulse broadening? Is that suppose if you transmit square wave, generally square wave becomes a Gaussian kind of pulse while propagation, and say this is at distance L1, at distance L2, if it is very higher distance, then slightly it gets broadened. Okay, L2 is very much higher than L1, and then L3, another distance, to be totally broadened, may happen, it is totally broadened. And suppose there are two such pulses, okay, this is two such pulses, and after long distance, they may get overlapped. So you cannot distinguish. So this is pulse broadening. So it cannot be distinguished. Two pulses cannot be distinguished due to pulse broadening. So to to overcome this, generally, to overcome this, many techniques are there. To overcome this, one, to overcome this, what happens? You may use single mode fiber. Okay, and this occurs generally in multi-mode fiber because mainly dispersion, okay, mainly in multi-mode fiber because many wavelengths propagate, many modes propagate. Single mode fiber, only one mode propagates. Okay. And many, generally you can also assume that many rays propagates in multi-mode fiber. And they have different speed. And single mode fiber is only one ray propagates. So that's why the same, there is no question of pulse broadening, but it still it exists, that is called intramodal dispersion. So there dispersion is of two kind, intermodal, okay, and intramodal. Okay, intermodal occurs in multimode fiber, and intramodal means within one mode still few wavelengths exist. Okay, generally within very narrow wavelength range, means few wavelengths propagates, and due to that intramodal dispersion or pulse broadening may take place, but it is very less significant. But in case of intermodal, it is severe. Okay, and it occurs in multimode fiber. So to avoid that, the pulse broadening, you can use single mode fiber. You can use graded index fiber, a GI fiber. All the rays travel at same speed. All the rays travel, generally different rays travel at different speed. That is the main cause. If we allow all the rays to propagate at same speed, then no pulse broadening. So that occurs in GI fiber, okay, and also can be overcome by special design of fiber that is called dispersion compensation fiber, DCF. Okay. The fiber structure will be such that it will be automatically dispersion will be reduced. Now next, what we'll see for this experiment digital link, what you have to do is very simple, that take some input frequencies of square wave, say it is 100 100 hertz, then you see the output how it is coming, then 500 hertz, okay, then output is take, then say another frequency is 100 kilohertz, okay. So you can see, you have to observe that what kind of square wave is appearing. Okay, it may get distorted, it may get broadened, but still since electrical circuit, you use the electronics, so due to the electronics you can the square perfectly square wave, generally it's not high frequency, it is very much impossible, very much difficult to generate high frequencies, a perfect high square wave for very high frequencies. So you have to observe what is the output and input waveform, okay, and you calculate the duty cycle T on and T off. Duty cycle you calculate for each case, okay, that is each case, that is T on by T on plus T off. So this is for the whole about the first experiment. Then for second experiment, you have to calculate numerical aperture. So in that experiment, what you have to do, that you have to use some light source, and this light source is coupled to optical fiber. Generally, some coupling schemes are there, different coupling scheme. Okay. You could have seen if you are present in the lab how the light source is attached with optical fiber. Okay, it is some jack socket type of thing is there. Just you have to insert over there. Okay, light source, then fiber, and you just project the light, okay, coming out of the fiber on a plain paper. Okay. And it will show some spot. Okay. So now if you know the distance between this height, okay, height and distance from the fiber end to the paper, this is paper, plain paper, and then if you use some trigonometrical Pythagoras theorem, okay, so it will make a triangle. So measure the spot size, the diameter, then you can get radius. You have to take some average readings, average value. Then if you know this height, okay, this height you know, okay, this height you know, and this angle is what? Can you tell this? What is this angle?
So critical angle.
Critical angle. Critical angle is present at core cladding interface. Okay. This is core and this is clad. If light enters at the core cladding boundary with critical angle, then it follows to the 90°. The light propagation is 90°. 90°. And this is theta c, but this is inside the optical fiber. And I am talking about outside. Can you tell what is this angle? And if you draw another figure, then you could have told this is optical fiber. And if light gets entered, then it travels. Then it will be totally internally reflected. But if this angle is critical angle, theta c, then this will propagate across the interface, core cladding interface. At that time, this angle is generally, you know, it is theta 0 max, a maximum acceptance angle. So this numerical aperture is what it is, sine theta 0 max, maximum acceptance angle. And if the light goes, if the light is in, and this is air, okay, where n0 is equal to 1, and this is numerical aperture is n0. So for normal, when the light is incident from air, then this is 1. So numerical aperture is only sine theta 0 max. So if light enters greater than the critical angle, this theta 0 max, then it will not be bound, it will go out from the fiber. So that's why it is called maximum acceptance angle. More than that, light cannot enter, and it will go out from the fiber core. It will not be totally internally reflected. For theta 0 max, for angle greater than incidence angle greater than theta 0 max, light will go out from the core. It will not be confined. And generally it is seen that you are correct in some sense that theta c critical angle is actually at that condition when the light propagates along the core and cladding interface. This is clad and this is core. And that time generally theta 0 at the incidence angle is theta 0 max. So this now light, since it is a light, actually it is coming in, it is going in the fiber. But at the same time, with the same angle, light comes out. Okay, that is theta 0 max. Okay, theta 0 max, same angle. So light traces its own path. Light retraces its own path. So this theta 0 max is nothing but this theta 0 max. Okay. So if you measure this height and you know the spot size, diameter, you calculate the radius, then using simple geometry, okay, sine theta 0 max is what? Sine theta 0 max is, say this is R and this is H. Then H by, no, R by, what happened? What will be the formula? What is the formula for sine theta? Anybody please tell?
So under root r square plus h square.
Yes, under root r square plus s square. So all these parameter you know, r you know from the spot, that is bright spot you will see. It is actually a spot, a light. It is a visible light. Invisible light में नहीं हो पाएगा, है ना? Visible spot. Say if you raise LED, LED light, okay, this is visible range. Then this spot will be visible. So measure this diameter of this plot and you know the height. Then you can calculate R by this ratio, R by R root over R square plus H square. So you can calculate the numerical aperture of the fiber. That is very simple experiment and very interesting. And value of numerical aperture is, I told you, for single mode fiber, it is near about 0.12. You have to note down this reading. For single mode fiber, it is 0.12. And also numerical aperture. Can you tell other formula for numerical aperture? Other formula for numerical aperture? Anybody? किसी को पता है?
Sir, under root n1 square minus n2 square.
Yes. What is n1? What is n1?
It is a refractive index.
Of refractive index of what?
Clad, sir.
No, यही तो ना गड़बड़ हो गया। सब जानने के बाद बोलोगे कि सीता कौन था राम का। गड़बड़ तो यहीं पे हो गया।
A denser medium.
यस, टेंशन मीडियम। तो टेंशन मीडियम किसका होगा?
Sorry, sir. Core
कोर
का
का।
medium.
हाँ, टोटल इंटरनल रिफ्लेक्शन हमेशा डेंसर से रेयरर मीडियम में जब लाइट जाता है तब होता है। डेंसर से रेयरर, तो कोर डेंसर है। n1 इज ग्रेटर देन n2। n1 का वैल्यू किस रेंज में है पता है कुछ? कितना वैल्यू होता है n1 का?
No, sir.
n1 का वैल्यू है 1.48 generally, 45 or 48, and it is at some wavelength, wavelength specific है। okay. For सिलिका फाइबर के लिए, ग्लास फाइबर इज 80, और N2 का उससे कम होगा। लेट अस से इट इज 1.44, स्लाइटली कम होता है थोड़ा। और अगर डिफरेंस ज्यादा कर दोगे तब न्यूमेरिकल अपर्चर क्या होगा? ज्यादा होगा कि कम होगा? If the difference between n1 and n2 is larger, then numerical aperture is more or less. कितना होगा बताओ? ज्यादा होगा कि कम होगा? डिफरेंस अगर ज्यादा है। कौन है? प्रनीश, प्रनीश बताओ। प्रनीश सुन रहे हो? हाँ, क्या बोल रहे थे हर्षवर्धन?
सर अपर्चर कम होगा सर।
अपर्चर नहीं, अपर्चर डिफरेंस,
यस सर।
डिफरेंस ज्यादा है।
यस सर।
n1 माइनस n2 ज्यादा है, तो क्या होगा? न्यूमेरिकल अपर्चर ज्यादा होगा, है ना? n1 माइनस n2 इट इज डायरेक्टली प्रोपोर्शनल।
यस सर, ज्यादा होना चाहिए।
ज्यादा होगा। और अपर्चर क्या होगा? कम होगा कि ज्यादा होगा?
सर अपर्चर कम होगा सर।
अपर्चर, अपर्चर ज्यादा होगा, क्योंकि इट इज प्रोपोर्शनल टू साइन थीटा। थीटा अगर ज्यादा है तो साइन थीटा ज्यादा होता है, थीटा अगर स्मॉल है तो साइन थीटा कम होता है ना?
यस
तो
यस सर।
यस, सो अगर डिफरेंस तुम ज्यादा ले लोगे तो वो एक्सेप्टेंस एंगल चौड़ा हो जाएगा, ज्यादा चौड़ा होगा और मोर लाइट प्रोपागेट करेगा। तो न्यूमेरिकल अपर्चर जो है मल्टीमोड फाइबर में एक्चुअली बहुत ज्यादा ट्रैवल कर, बहुत ज्यादा लाइट रे घुसता है, बहुत बड़ा होता है ना साइज, कोर साइज बहुत बड़ा होता है, और कोर डायमीटर। और न्यूमेरिकल अपर्चर भी बड़ा रखना पड़ता है मल्टीमोड फाइबर के लिए। हाँ, मल्टीमोड फाइबर के लिए न्यूमेरिकल अपर्चर थोड़ा ज्यादा रखना पड़ता है, सो दैट more light can be accepted, more rays or more mode can be accepted, can enter, more mode can enter. मल्टीमोड फाइबर ऐसे नहीं कि खराब है, वो हमें वो भी उसका भी अपना एडवांटेज है, बहुत सिंपल एंड लेस कॉस्टली है, लो कॉस्ट है, क्योंकि वो साइज ज्यादा है, साइज बड़ा साइज फैब्रिकेट करना इजी रहता है, स्मॉल साइज फैब्रिकेशन माइक्रो फैब्रिकेशन डिफिकल्ट होता है, सिंगल मोड फाइबर कॉस्टली होता है बहुत, इसीलिए मल्टी मोड फाइबर से, क्योंकि उसका कोर डायमीटर है 8 to 10 माइक्रोमीटर होता है और उसका मल्टी मोड का 50 माइक्रोमीटर से ज्यादा होता है कोर का डायमीटर। सो इसीलिए सिंगल मोड फाइबर का न्यूमेरिकल अपर्चर फॉर सिंगल मोड फाइबर it is in this range less 0.12, whereas multi-mode fiber numerical aperture is generally 0.3 to 0.5 or even more than that. ये एक difference है, so difference is not in the size for single and multiple but also in the numerical aperture in case of single mode and multi mode. ना अभी दूसरा एक्सपेरिमेंट है, अभी सिंपली ये सब बेसिक्स था, अभी हाँ उसका और एक पार्ट है फाइबर एटेन्यूएशन, ठीक है, तो फाइबर एटेन्यूएशन का दूसरा पार्ट है सेकेंड एक्सपेरिमेंट। इसमें क्या है कि फाइबर एटेन्यूएशन मीन्स लॉस ऑफ लाइट, लॉस ऑफ light energy, loss of light energy. So what are the different reasons of fiber attenuation? One is absorption, and one is scattering, and another is bending loss. Absorption means absorption is due to absorption by fiber molecules. Okay. So the fiber molecule itself absorbs the light. So if that light is what? It is composed of photons, photon energy, light energy, particles, photon particles. So एक fiber molecule, one fiber molecule absorbs one photon, then what will happen? There is number of photon will be reduced. So this light energy will be reduced simply. So if it occurs due to absorption of light due to occur by fiber molecules, okay, and it may be also intrinsic or extrinsic. Intrinsic or extrinsic, this we will study in the theory. Intrinsic means agar if silica, the basic constituent fiber molecule, if absorbs the light, then it is called intrinsic absorption. And if some external material which is used, which comes during the fiber fabrication, external material that acts as impurity, okay, impurity or doping, you have to do doping for fiber. This is necessary because you have to change the refractive index during fabrication. Change of refractive index from coat to clad एक ही चीज है, एक ही सॉइल मटेरियल है, उसी को हमको कोर बनाना है, उसी को क्लैड बनाना है. This is solid material. Say it is a glass. So glass is pure silica. Okay, pure silica. So it is having refractive index 1.4. Say 48 or 1.4, say let us say it is 1.545. So for core, say you have to make it 1.45. So for clad, let us you have to keep it, you have to make it lesser, say it is 1.44. So this can be done by doping. There are several atoms which can increase or decrease the refractive index. So this is doping is used. This is used for changing the refractive index. Okay. So I am not going into the process how it is, how it has changed fiber silica. So my point is here to discuss that what are the different reasons that reduce that absorbs the light energy, that absorbs the photon. So it may be internal material or fiber material, SiO2 silica, or some other material which comes as impurity during fiber fabrication. And also you know that OH minus hydroxyl ion, this is a killer ion that introduces during, say if you heating, during heating oxidation, it appears. So it absorbs the light very much. So there is a deep at 1200 nanometer, 1200 nanometers. So there is loss due to this. Now scattering is what? Since it is a amorphous medium, okay? That means it is non-crystalline. So somewhere there is change of refractive index. The refractive index is not uniform. So that makes what? Non-uniform refractive index. Non-uniform refractive index. So due to that, light scattering occurs. You know that blue sky is what? Is due to Rayleigh scattering. Rayleigh scattering. That is nothing but in the air there are different layers and which have varying refractive index. So this varying refractive index across some region, okay, so that scatters the some particular wavelength which is comparable, maybe lesser or maybe greater than the length over which the refractive index varies. Although if it is step index fiber, if it is step index fiber, we say that it is constant. Refractive index is uniform throughout the core, but actually, practically, it is non-uniform. There is slightest change. If it is the slightest change within micrometer range, then also that particular wavelength will be not be able to propagate. It will be scattered. So that times in that case it will be, so loss curve you study when you study this attenuation characteristics, then alpha, yeah, alpha dB per kilometer, this one. So you see that for single mode fiber it is less, multi-mode fiber it is high. Okay, so it is I think 0.1 dB per kilometer in this range for glass fiber, and multi-mode fiber it is slightly higher, 3 dB or more than that. You have to check it, okay, whether what is the value. So we will calculate using some basic experiments. How we'll do? We use we use fiber of different length. Say it is 0.5, 5 meter, okay. 0.5 meter, 1 meter, 5 meter, and 10 meters, let us say. And we use light source and light detector. Here, let us, to avoid confusion, let us say it is photo detector. Otherwise, you will confuse. So, for different length, input voltage is fixed. But if you change the fiber, the output voltage, detector output will vary. If fiber length changes. Okay. So you have to draw one graph here, 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 here. You have to draw a straight line, and here you have to take 2 points or any 2 points, V1 and V2. And using some formula of alpha, that is 10 log V1 by V2 divided by length. What is this length? Okay, this is the difference. Okay, delta L, say this is delta L. This is length versus output voltage. So this is coming to be dB per kilometer or meter. So this way you have to do the second experiment. Then third experiment is PWM and PPM. So there is basic kits based on that here using that kit we will transmit pulse modulated pulse with will simulate or realize the pulse with modulation and demodulation, different signals at the input, different signals at the output. So we'll study in block diagram form, and we'll see the waveforms, how the pulse width modulation and pulse position modulation takes place, but in optical fiber. You may have seen through electrical wire, but we will see here through optical fiber how they propagates. Then for another experiment, that is time division multiplexing. You know that basic concept of time division multiplexing, that one clock signal is taken, okay, and at different clock pulses, different input signals are transmitted one by one sequentially, okay, so that they are multiplexed in one line, one channel, and they are sent. So here pulse sampler, then so it is basically analog TDM. Then another experiment is digital TDM, where digital signals are transmitted by means of some framing. There is some frame, and that starts with marker. So the marker are basically, it is a it is one frame. So there are two markers of 8 bits. Okay, 8 bits. Generally and this is one frame. So there are some slots, and then another frame starts, M1 and M2. So there are some slots for channels. This number of channels may be 4 or 8, whatever it is. So data from each channel, and all the slots are of 8 bits. Okay, 8 bit, 8 bit, 8 bit, 8 bits. So you have to calculate the frame width. Frame width will be how much? And observe the waveform and calculate the frame width. Now suppose you transmit 4 kilohertz audio signal. Okay, audio signal through 4 kilohertz, maximum frequency if it is 4 kilohertz, then sampling frequency is greater than equal to 8 kilohertz. Okay, so that means 8,000 samples per second are transmitted, or 8,000 frames would be per second would be transmitted. So that means one frame duration is equal to 1 by 8,000. So that means 125 microsecond. This is frame duration. And similarly, channel bit rate, you have to calculate bit rate. Okay, bit rate is how much, and some other parameters in this experiment. The next experiment is on Manchester coding and decoding. The next experiment is Manchester coding. Generally in Manchester coding, what happens at the middle of the beat, there is transition of the signal, and similarly for one is high to low at the middle, and for this logic 0 there is 0 to high, 0 to means low to high. This is the Manchester coding. Now this depends on clock pulse. Okay. And suppose we say, let us say this is your data. Okay, and we use many clock pulses. Many clock pulses. Okay. Now each clock pulse we assume as symbol. Okay. Now at the half of the clock pulses, there will be transition. Okay. For Manchester coded data. So we'll show the waveform, how they work, how they get transmitted. Okay. There are some advantages, disadvantages. The next experiment will be beat error rate. Uh, Basically, here we'll also see the eye pattern. Okay. Eye pattern is nothing but your suppose uh, the a series of a series of 1 0 1 and 0 are transmitted. Then if you trace on a CRO, if all they remain same, then their transition rise time and fall time. The rise time and fall time, okay, will occur at same time. That means several times the same waveform are superimposed on a screen. Then it will look like a eye. So if the signal is good, then eye pattern will tell you that from the eye pattern you can see the how good is the signal. If it's a good quality signal, if it is like this, that they are means they are not aligned, okay, dispersed, the rise time and fall time are not same, are not occurring, the transitions are not occurring at same time, so that means bad quality signal transmission. So eye pattern will tell you many things. It is used highly in digital communication system. Okay, eye pattern. Then beat error rate is what? Number of beats with error divided by total number of beats transmitted. Okay, during fixed time. During a fixed time. That will tell you beat error rate, and this is generally 1 by 10 to the power 9. High, if BR means 10 to the power minus 9, so it is very good. 1 bit out of 10 to the power 9 bits is in error. So it is very good propagation or communication. The next experiment is related to WDM and DWDM system. So what is WDM? Is that wavelength division multiplexing. So in electrical communication, it is actually equivalent to FDM, frequency division multiplexing, where different channels are connected with different light source. Okay. So it is lambda 1. So there are say there are 4 wavelengths, lambda 1 light source. There are say so light source, all are light source, lambda 1, lambda 2, lambda 3, lambda 4. and different channels, say 4 channels, channel 1, channel 2, channel 3, channel 4. So all the light will be combined. Okay, then they will transmit it to fiber, and again there is another device that will decouple this, and there is photo detector that will detect a particular wavelength. Okay. Lambda 2, lambda 3, lambda 4, and this is channel 1 decoded 2, 3, 4. So this should be coherent light source. That means laser source. And this should be single mode fiber. Single mode fiber. So, and generally this one channel is capable of transmitting thousands of channels. So within this 4 wavelength, using this 4 wavelength WDM system, so lakhs of channels can be transmitted over single fiber. Nowadays, 100 wavelengths, 120, I think. So it is developed step by step. Since 1980, it was, or 1990, it was 2 wavelength. Then 1990, 4 wavelength, 2 wavelength system, 2 wavelength WDM, then 4 wavelength WDM, 2000, more than that. Okay, then 8 or 16. Then nowadays, nearly whole world is using nearly 120 wavelengths. Okay, generally this range. You see in the internet that nowadays WDM takes place. It is called DWDM, dense wavelength division multiplexing, dense WDM. So more than near about 120 wavelengths are capable of handling data transmission throughout the globe. And all the fiber cables are laid under the sea, very deep under the sea. Okay, so all are using this WDM system. Okay. The 9 and 10 experiment. 9 experiments I told about that linearly polarized modes. Okay, those modes will be visualized using LP modes. So you have to use this formula V number K0A into numerical aperture, where K0 is, so basically it is 2 pi by lambda into fiber radius. Okay, this A is fiber radius. And numerical aperture is root over n1 square minus n2 square. Okay. So one software is used, that Artsoft, very big company Artsoft. Nowadays Synopsys, have you heard the name Synopsys?
Yes, sir.
Yes.
Yes.
So yes. So Synopsys now purchased, it is Artsoft is coming under Synopsys, and they are designing they have given us the software. Earlier it was this, so it is a fiber design software. If you would have present here, then we could have done some project, okay, fiber design software. Okay. So here they have they use some window. Okay. So generally one window will appear when you run the software, and some axis will be given to you. Okay. Dot line background dot line है. तो यहाँ पे क्या करना है, इसको खींच के, ये तो टेढ़ा हो गया. हाँ, इसको खींच के ये करना है, स्ट्रेट लाइन ड्रॉ करना है. लेट अस से इट इज ए स्ट्रेट लाइन. मान लो यहाँ तक हम किए, तो ये कोर हो गया. हाँ, ये कोर हो गया, और ये जो है ये फ्लैट हो गया. और फाइबर, तब फाइबर ये टोटल, ये तक फाइबर का लेंथ है, टोटल फाइबर यहाँ पे फाइबर लेंथ है. ये कोर हो गया, इसका डायमीटर दिस इज 2a. ये भी सब पैरामीटर्स हम लोग को देना रहता है इसमें. तुम लैम्डा दो 1.55 से माइक्रोमीटर, n1 दो 1.45. इन एक्चुअली कोई भी एक दे सकते हैं, आइदर n1 और n2. जनरली n2 देते हैं, तो n2 अगर से 1.45 देंगे, मतलब बैकग्राउंड रिफ्रैक्टिव इंडेक्स. n2 हो गया बैकग्राउंड रिफ्रैक्टिव इंडेक्स. So n2 अगर 1.45 है, so generally numerical aperture can also be written as generally n1 into root over 2 delta. Okay. Or if it is a single mode, then n1 or approx, you know that for single mode fiber n1 is approximately equal to n2. बहुत कम difference है. This delta, which is index difference, relative index difference, n1 by n2, n1 minus n2 by n1. It tends to 0, very small, near about 0.001. So in that case, it acts as single mode, LP modes. Generally, LP modes propagates in these conditions when n1 is approximately equal to n2, and this is called weakly guiding approximation. Generally, n1 n2 से ज़्यादा होता है. But if it is close to n2, then some part of the light penetrates into the cladding during propagation. So that times guiding अच्छा नहीं होता है, light guiding. So उसको बोलते हैं weakly guiding. Guiding weakly हो रहा है, light guiding. So weakly guiding approximation में ही LP modes travel करता है, where n1 और उस condition में generally how this LP modes actually generates. बाकी कंडीशन में LP मोड जनरेट नहीं करता है फाइबर में. बाकी कंडीशन में TM मोड प्रोपागेट करता है, और HEH इंडिविजुअली और कंबाइंड होके फ्लो करता है. लेकिन LP मोड में इसका कॉम्बिनेशन फ्लो करता है. तभी कंबाइन करेगा जब उसका बीटा वैल्यू, जो प्रोपागेशन वेक्टर है, बहुत मैच करता है. वही मोड्स कंसीडर होगा जिसका प्रोपागेशन वेक्टर बीटा वैल्यू इक्वल होगा, ऑलमोस्ट सेम, और वही मोड कंबाइन होकर एक नया मोड जनरेट करता है. दैट इज कॉल्ड LP मोड्स, लीनियरली पोलराइज्ड मोड्स. लाइट प्रोपागेशन बहुत डिफिकल्ट है फाइबर में. और सो उस कंडीशन में ये एक्चुअली n1 इज अप्रोक्सीमेटली इक्वल टू n2. सो इसको हम लोग लिख सकते हैं n2 इज, और एग्जैक्टली अगर लिखेंगे, लेट अस स्लाइड. N2 by 1 minus delta. Actually is using this formula. N2 is N1 is equal to N2 by 1 minus delta into 2 delta. So इस सॉफ्टवेयर में हम लोग दे दिए लैम्डा, हम लोग दे देंगे N2, हम लोग दे देंगे 0.001 डेल्टा इंडेक्स डिफरेंस, और लाइट सोर्स सिलेक्ट करेंगे. विल सिलेक्ट द लाइट सोर्स, देन विल विजुअलाइज द लाइट प्रोपागेशन. सो उस तरह से प्रोपागेट करेगा. एक विंडो आएगा जिसमें हम लोग देखेंगे कि एक गॉसियन टाइप का लाइट जा रहा है. ऐसे ऐसे करके लाइट प्रोपागेट करेगा. And the condition is that field tail must exist. कोई भी लाइट प्रोपागेशन जब होता है, ये कोर है and this is clad. Field tail, this is field tail must be present, otherwise light will not propagate. So field tail exist कर रहा है, कोर में maximum intensity, so इस तरह से वो propagate करेगा. And this is LP01. And LP11 के लिए क्या होगा? ये LP01 मोड ट्रैवल हो रहा है. LP11 के लिए क्या होगा? दो लाइट पीक जाएगा, एक ऐसे ऐसे करके, मतलब एट डिफरेंट डिस्टेंस. दिस इज Z, दिस इज Z फाइबर लेंथ. ऐसे ऐसे LP11 में प्रोवाइड करता है. So as the order of the mode increases, the number of peaks will also increase. LP31 के लिए और ज्यादा पीक होगा, हो सकता है 3 पीक आए. So now this is LP01. Now what we have to do? We have to vary in this equation, that is B is equal to 2 pi by lambda into A into numerical aperture. We just vary A, fiber radius. So fiber radius, if you vary, then what fiber diameter will increase. Okay. This way. So that means V number will change. You have to calculate V number for different, okay, for different value of radius. V number will change, and you can measure the power scale of light from the window. And if you plot this, okay, if you plot this, you will see this kind of graph where V number, this is V number, okay, and this is P core by P in, that is mode power, okay, light power normalized, light power normalized. Okay, so just you have to take these conditions from 2 to 6, and this is the graph for LP01. Okay. Generally और एक ग्राफ होगा LP11 के लिए. ये 2.405 से LP11 स्टार्ट होगा. Next higher order mode. So before LP number 2.405, only LP01 propagates. So this software you can see, and next experiment is your same software, that is Mach Zehnder electro-optic modulator. What is electro-optic modulator? That it converts, that is called EOM, electro-optic modulator. That is widely used for very or ultra high frequency application. Suppose your input signal is its RF signal, okay, that is in the range of gigahertz. You cannot use transistor to modulate the light source. You cannot handle LED using transistor at that frequency because they will fail. High frequency, they will all be short circuited. The capacity we trigger short circuit. So they generally, this is the limitation for any high frequency electronic circuit. So you cannot, but your signal is, so this is RF signal. RF signal that is in the range of gigahertz or more than that. So how you can convert the electrical signal to optical signal? Basically, it converts the electrical signal to optical signal at high frequency, very high frequency, gigahertz, not kilohertz or megahertz, gigahertz range. So in that case, generally, this simple circuit, this is called Mach-Zehnder modulator is used. It is an waveguide, okay, not an electronic circuit. It is what? It is waveguide, okay. So this light in, this is a laser, okay. You connect one laser, high frequency laser. This is about terahertz. Okay. This is terahertz frequency, 200 terahertz, or 1550 nanometers, near about 200, 1550 nanometers. Now here we apply, we connect some electrode, okay. Electrode where we apply, where we connect the RF signal. So this is grounded. One part is, so only one arm, so there are two arms, okay, two arms. It is called MZI, Mach-Zehnder, Mach-Zehnder, Mach-Zehnder modulators or Mach-Zehnder interferometers. So there are two arms in this Mach-Zehnder interferometer. So light is splitted in two paths, okay, and again they meet and come out. This is light, okay, modulated light. That means the intensity of this light is according to the RF signal applied, whereas the input laser is the carrier signal. Laser light is the carrier signal. Now how it is, what is the basic principle is that waveguide made from lithium niobate crystal, LiNbO3, lithium niobate crystal. What is the property? of that, if voltage is applied, it changes refractive index. Okay, so that means if this voltage is say RF signal, so it will change the refractive index, and since there are two arms, you can see there are two arms, one another. Here refractive index gets changed, here no change. No change of refractive index because we have not applied any voltage through the no electrode is there. So due to this refractive index, phase gate change. Okay, phase gets changed. So one light, say this is P1, it is having different phase than P2. So there are two light having different phase. So what we can write? So two lights propagating with different phase, so they may interfere constructively or destructively. Okay, so if they constructively interfere, then you will get light. If they destructively interfere, then you will not get any light. So that means the if you plot the phase difference delta phi between two lights between P1 and P2, okay, then depending on the phase difference, light coming out the fiber end or waveguide end will be either high or low, okay, or will depend on the phase difference. So that phase difference is actually is dependent on applied voltage. Okay. So if you change the voltage, the phase will change accordingly and you will get accordingly the light, and light intensity will depend on the applied voltage. If it is sinusoidal, if the input voltage is sinusoidal, okay, then phase change will be sinusoidal and output signal will also be sinusoidal. So generally some linear range is considered, this linear range, okay, for operation. Now here you have to draw this waveform, draw this waveguide in this in our software. Okay, draw this waveguide and simulate various parameters. So there is also here application in sensing, Mach Zehnder interferometer. We can so this is actually RF signal you are applying, but at the same time If it is made, this is waveguide. Okay. If it is made from fiber, okay, if it is made from fiber, optical fiber, if this say simple, uh, if you use simple optical fiber, then it can act as sensor, fiber optic sensor. Suppose you apply some force at one arm. Okay. So here some coupler is used, okay, and here coupler. It is 1:2 and here 2:1 coupler. So these are all fibers are joined through the coupler. Okay. Then if you apply force, the fiber, according to the principle of fiber optic sensor, the phase NKL, if you apply force, then L, if you, that means length will change, length of fiber will change. Okay. Length L will change if force is applied. So if force is applied, then power will vary according to the phase or according to the force applied. So it may act as sensor. Light out power output will change according to the applied force. So Mach-Zehnder interferometer have lot many applications, not only communication but in sensors and many measurement of length. This is very sensitive instrument or device. Okay, very small length it can be detected. Okay, very highly sensitive. So then another software will be dealt with, that is Manchester coding. Manchester coding, OptiSystem. OptiSystem software, another software we'll use. OptiSystem. Here, whole optical communication can be simulated. Optical communication techniques can be simulated using this software. So here we implement, only, here we will implement that, which one, that is Manchester coding technique for understanding Manchester coding. For example, okay, so manual it is given, we'll demonstrate you, or you can download it and it is valid for 1 month, but do not download it now. At the end of this session or semester, you can download and simulate it, because it is limited time duration license. Then Manchester coding ho gaya. Then another is, last experiment is fiber amplifier, EDFA, RBM doped fiber amplifier. So here we have hardware kits for that fiber amplifier. Basically, if you say after transmission of signal, the signal may get lost. So you have to generally we use repeater to restore the signal. But if you use repeater, then you have to involve electronics. But so again, electronics have some limitations. So to avoid electronics, generally this type of fiber amplifier or semiconductor optical amplifier is used, so that during the propagation of light through the optical fiber, the light will be automatically amplified. So this is say your optical fiber, and some portion of the optical fiber uh, generally this doping with erbium ions is performed, is provided, erbium ions. So this actually uh, used for pumping mechanism. You know that the light amplification takes place in laser through the means of stimulated emission. So you know that stimulated emission, that pumping is required. Okay. So this pumping of molecules by applying external energy. So 980 nanometer wavelength is used, and this is your 1550 nanometer incoming wavelength. Okay, incoming wavelength for your data or information, and this is pump wavelength. So stimulated emission takes place. Okay, and stimulated emission tells that the molecules are uh, pumped to higher energy level, and if some photon is incident, then that photon will be released as well as another photon will be emitted. So one photon will emit to another photon. So that way light is amplified. Okay. So this fiber amplifier is a special kind of fiber where some doping region is used, doped with erbium ions. Okay, so if light travels through this region, it is automatically amplified. Amplified light will get. So this hardware kit is there. We'll try to demonstrate this. Okay. So now so we have finished or explained all the experiments. So do you have any doubt? And I have recorded also, as you have requested. Harshvardhan?
No, sir, I don't have any doubts. Thank you, sir.
Okay. Anybody else?